In this video, we'll take a look at the equation of a plane and actually three different kinds of equations. So first of all, this yellow thing is supposed to represent a plane. It's actually, this isn't the entire plane. It does extend in all those directions infinitely, so this just really represents part of a plane. Now, we're going to talk about vector and parametric equations first. So let's say that we have this arbitrary point in the plane. I'm going to call it the point x, y, z. So x, y, and z could be any point whatsoever. Now, one way to define that we're talking about this specific plane is if we have a particular point in the plane, like -3, 4, 5, this A point, and two vectors that are in the plane or parallel to the plane. Those actually mean the same thing, like the vectors u and v here. Now, this arbitrary point is in the plane if the vector that goes from -3, 4, 5, where the tail of this vector is, to that vector x, y, z, if that vector is also parallel to the plane. Now, we would know that that vector AP is parallel to the plane if we can write that green AP vector as some linear combination of the vectors u and v. So, for example, the way it's drawn here right now, it looks like that AP vector is 3 vector v's plus a vector u, and that's the parallelogram law, or you could look at half of it as the triangle law. And so AP is in the plane, okay, if you can write that vector as some linear combination of the two vectors that are in the plane or parallel to the plane. Now, let's draw a vector that goes from the origin up to A and also from the 0, 0, 0 point up to point P. And so we're looking at this triangle here right now. Now, the vector that goes from O to P, which is OP, is equal to OA, this one here, OA, plus the green vector, which we would call AP. So that's just a triangle law, OP equals OA plus AP. Now, as I was talking about when those u and v vectors were here, the vector AP is in the plane if you can write it as some linear combination of the vectors u and v. So s and t here are scalars. So that's what I mean by it's some amount of vector u's plus some amount of vector v's. The way we drew it, I had 3 vector v's and 1 vector u. So s and t are just scalars or parameters. And so that's just writing that AP vector as some number of vector u's plus some number of vector v's. Now, I'm going to substitute in place of the AP SU plus TV. And so this is in general what a vector equation, the structure of it looks like. And so this is how we would write our vector equation. This is just the structure. This is what it would look like. Now, OP is a vector that goes from the origin to this arbitrary point x, y, z. So this OP vector would be the vector x, y, z. Remember, when you find the vector between 2 points, you subtract the coordinates. So O, or the origin here, is 0, 0, 0. When you go x minus 0, y minus 0, z minus 0, then we would call that the vector x, y, z. OA is the vector -3, 4, 5 because it goes from the origin to the point -3, 4, 5. So that's OA. And then SU plus TV. So S times vector U, which is a 6, -5, 1 vector, plus T times vector V, which is a -1, 3, 2 vector. So that's what a vector equation looks like. It looks a lot like the vector equation of a line, except you have another parameter here because a line is only a one-dimensional thing, whereas a plane is two-dimensional. So you need 2 vectors in the plane as opposed to 1 vector just parallel to a line. So that's what a vector equation looks like. Now, if you take that vector equation and solve for x, solve for y, solve for z, that gives you the parametric equations. So x would equal -3 minus s plus 6t. For y, y would equal 4 plus 3s minus 5t. And z would equal 5 plus 2s, multiplying the s in, plus t. So that's the parametric equations. If you write them all in the same order, and you're always supposed to, the first constants represent the coordinates of a point on the plane, or the components of a position vector for the plane, and then the coefficients of s and the coefficients of t are the components of 2 vectors parallel to the plane. In this first example, we're asked to find parametric equations for the line passing, or the plane, passing through these 3 points. So to find parametric equations or vector equations, you need two vectors in the plane. So, or parallel to the plane. So we could find, for example, the vector DE, so the vector that goes from D to E. And remember, you subtract the coordinates. So 3 take away -2 is 5, 0 take away 6 would be -6, and 8 minus 1 would be 7. So those are the components of vector DE. EF would be the vector that goes from E to F. So we subtract the coordinates and we would get EF to be -7, 2, 1. Now, I could use different vectors. I could use, instead of DE and EF, I could use, for example, DF or FE. FE would just be the opposite of this. But any two vectors that are parallel to the plane will do. So to write the parametric equations, they would look like this. X, Y, Z equals. Now, remember the constants here represent the coordinates of a point on the plane. So I used D. I could have easily put 3, 0, 8 here, or -4, 2, 9, but I used the coordinates of point D. And then the coefficients of S here are the components of one of the vectors parallel plane. I use the DE here, and the -7, 2, 1 are the components of the EF vector. So that's what the parametric equations for this plane could look like. And of course, you have different options for these numbers. A little summary page on this before we get to a few more examples. So for each of the following, the plane contains the point A1, A2, A3 with direction vectors U and V here. And T and S are scalars. They're parameters. Could be any real numbers whatsoever. So the vector equation looks like this. X, Y, Z equals the vector A1, A2, A3. So that, now I've written that as a vector. Square brackets mean a vector, but it also can represent the coordinates of a point on the plane. It's written as a vector because if we go back to this, remember, that's actually the vector that goes from the origin to a specific point on the plane. So that's how you actually interpret it, as a vector. Okay, so let's go back to our summary here. There we go. Plus S times a vector parallel to the plane plus T times a vector parallel to the plane. That's what the vector equation of a plane looks like. So you need two vectors in the plane, and you need to know a point on the plane. Parametric equations look like this, and again, these first constants represent the coordinates of a point on the plane, or the position vector of a point on the plane, and then the coefficients of S and T here are the components of two vectors that are parallel to the plane. Now, another kind of equation which is very useful in certain circumstances is the scalar or Cartesian equation. Cartesian is actually named after the mathematician and philosopher René Descartes. That's where the Cartesian comes from. Now, instead of defining a point in the plane and two vectors parallel to the plane, you could instead say, well, instead of two vectors parallel to the plane, you could say, well, I could define that this is the plane I'm talking about by, I know a point in it, so I still need the point, the -3, 4, 5, for example. And instead of two vectors in the plane, I could say, well, instead, I'll sort of specify the direction the plane goes by specifying a vector perpendicular to it. So instead of two vectors in the plane, I don't really need the U and V then. If I know a vector perpendicular to the plane, then I'm just talking about this particular plane. That's what we mean by defining a plane or describing a plane. I mean only this yellow plane. This yellow plane is the only plane I'm talking about that contains this point and has this vector that's perpendicular or normal to it. So that's another way to define that I'm talking about a specific plane. Now, this again, here's our arbitrary point X, Y, Z. And in order to get that normal vector, what we're going to do is take the cross product of the two vectors that are in the plane. So if I'm doing the cross product of these, I would list the okay, I've got the vector 6, -5, 1. So we start with, remember, with the y component and then the z component and the x and then back to the y. And similar for v, so we'll go 3, 2, -1, 3 here. And so to get my normal vector, I'm going to take the cross product of this. And so this and this is how we'll get the equation in just a little bit here. This vector that's in the plane is in the plane if that vector is perpendicular to our normal vector, and we'll use that in the next page to get the equation. So we're going to do the cross product now. So u cross v will equal, so this would be -10 minus 3 and then negative 1 product minus 12, and then 18 minus 5. And so that gives us negative 13, negative 13, 13. Now, that's a pretty long vector. Any multiple of that will do. So, for example, I could divide out a 13 or a negative 13 and make this shorter and still perpendicular to the plane. So instead, I'm going to divide it by negative 13. I'm going to use the vector 1, 1, negative 1. If you really want to, you could make this negative 1 and this negative 1, this positive 1, and that would be fine too. So on the next page, again, we're going to address this perpendicular vector here. This is normal to the plane if the dot product of this vector is in the plane if the dot product of the normal and it equals 0. And we're going to use that to get the equation here. It looks quite different than the vector and parametric one. So again, here's our vector. So the normal vector 1, 1, negative 1, and the dot product of the AP vector should equal 0 because if this vector is in the plane, it has to be perpendicular to the normal vector for the plane. Now, the vector AP is the vector that goes from negative 3, 4, 5 to the arbitrary point x, y, z. So we subtract the coordinates to get the components of the vectors. So x take away negative 3 is x plus 3. Y take away 4 is y minus 4. And z take away 5 would be z minus 5. And so that's the vector AP's component. So we're going to take the dot product of the n and AP. And this will actually give us the equation when we simplify it. So 1 times x plus 3 is x plus 3 plus 1 times y minus 4, which is y minus 4, plus negative 1 times z minus 5. Well, negative 1 times z is negative z, and negative 1 times negative 5 is plus 5. And we have three constants here, 3, negative 4, and 5. And that adds to 4. 3 minus 4 is negative 1, plus 5 is 4. So simplifying the constants, we get x plus y minus z plus 4 equals 0. And that's the scalar equation that we're looking for. Now, notice that the coefficients of x, y, and z are 1, 1, and negative 1. And it's not a coincidence that those three numbers are the components of the normal vector. And that's one of the main advantages of this equation in certain circumstances. The coefficients of x, y, and z, if it's written in this form, everything on one side set equal to 0, are always the components of a vector normal or perpendicular to the plane. And so that's a little summary in this page before we finish with another example. The scalar or Cartesian equation of a plane has the form ax plus by plus cz plus d equals 0, where the coefficients of a, b, and c are the components of the plane's normal vector, or they're parallel to the normal vector. So in this example, it says find a scalar equation of the plane with normal vector 3, negative 2, 6 and containing this point. Well, if 3, negative 2, and 6 is the normal vector, then they're the coefficients of x, y, and z in the scalar or Cartesian equation. So the equation would be 3x minus 2y plus 6z plus some constant that we'll call d for a moment until we find what d is equals 0. Now the way we find d is this point is supposed to be in the plane. So if this point satisfies the equation of plane because it's supposed to be on the plane, then we can substitute to find d the negative 4 in place of x, the 1 in place of y, and the 2 in place of z, because if that point's on the plane, that better satisfy the equation, which means that if we substitute in, it should make both sides the same. And so if we expand this out, that's negative 12 minus 2 plus 12. Well, these opposite 12 and negative 12 would just add to 0. And so we get negative 2 plus d equals 0, so d would have to equal 2. And so putting a 2 in here, then the equation of the plane, or a scalar equation of the plane, would be 3x minus 2y plus 6z plus 2 equals 0. Now the reason why I said a equation, because there's more than one way to write this. Like any multiple of this is still a scalar equation of this plane. So for example, if we'd used, instead of 3, negative 2, 6, if we'd used, let's say we multiplied it by 2 and used 6, negative 4, 12. Well, that's still going to work. It would just be 6x minus, multiplying by 2, 6x minus 4y plus 12z plus 4 equals 0. And that would still be a scalar equation for the plane. Example 3, and there's more than one part to this. That's why we start with A here. We've got a plane that goes through these 3 points. So we're going to kind of draw everything together here. We're going to talk about vector and parametric here, and then we're going to get into scalar equations as well. Find vector and parametric equations for this plane. So to find vector and parametric, you need two vectors in the plane. So if we could, for example, find the vector AB. Remember, it goes 0 minus negative 3 is 3, 2 minus 4 is negative 2, and 5 minus 1 is 4. So that's AB. So let's also find AC. Subtracting the coordinates, we get AC to be the vector 6, 2, negative 3. Now, I could have done BC instead of one of these. It really wouldn't matter. So a vector equation, a possible vector equation is, and it's x, y, z equals. Now, this is the position vector of any one of the points on the plane. So I use B, but I could have easily had negative 3, 4, 1 here, or 3, 6, negative 2. It wouldn't matter. And so S times the AB vector plus T times the AC vector. S and T are often used for the parameters. You can use other ones as well. It really doesn't matter, but you use the S and T used a lot. To write a possible set of parametric equations could look like this. So if I write the ones out for this vector equation, I would have 0, 2, and 5 at the beginning. So 0, I don't really need to write a 0 there, 2, 5. And then 3s plus 6t here, negative 2s plus 2t here, and then s times 4 is 4s, and t times negative 3 would be minus 3t. So there's the parametric equations that go with this vector equation. In part B here, same 3 points, we're asked to find a scalar equation. So a scalar equation needs the normal vector for the plane. So I'm going to use the same 2 vectors from the previous page, and we're going to find the cross product of those because that gives us the normal vector. And so if I'm doing these, so I would go using this particular formula, negative 2, 4, 3, negative 2 here, and then 2, negative 3, 6, and 2. And so we go negative 2 times negative 3 is 6, which is that 6 there, minus the product of 2 and 4 is 8, comma, and then this would be 24, minus negative 9 would be plus 9, and then this would be 6 right here, and then minus negative 12 would be plus 12. And so that simplifies to negative 2, 33, and 18. So those are the components of a vector perpendicular to the plane. So they are the coefficients of x, y, and z in the scalar equation we're going to find here. We need just to find D now. And so we can use any of these points. It really doesn't matter which one. I'm going to use B. I'm going to put 0, 2, and 5 in place of x, y, and z, but I could have easily used negative 3, 4, 1 or 3, 6, negative 2. It wouldn't matter. For all of those, you would get the same D value. So negative 2 times 0, of course, is 0. 33 times 2 is 66, and 18 times 5 is 90. 66 and 90 add to 156, so D would have to be negative 156 to make this equation, the left side, equal to 0. And so if we put negative 56 in here, we get a scalar equation to be negative 2x plus 33y plus 18z, and then minus 156 equals 0. Now, if you, a lot of times in textbooks, they'll keep this leading coefficient positive. So if you want to write positive 2x minus 33y, so I'm multiplying everything by negative 1, minus 18z and plus 156 equals 0, that's just as fine. Now, one last example here, C here, we're asked, are the points D and E on this plane? Now, if you're using the vector or parametric, actually parametric are the easiest of those, you would be substituting negative 2, 4, 3, and then 24, 4, and 4 in place of x, y, and z and solve for. Actually, let me go back for a second here, just so, you would substitute those coordinates from the point in place of x, y, and z, and then solve to find if there's a single value of s and a single value of t that gives you those points. And that's a bit long. You can use elimination or substitution for that, but this is the nice thing about the scalar equation, is it's a lot simpler to figure out if a particular point's on a plane or not. You don't need to solve for s and t in those parametric. So what you do is you take the scalar equation that you have and you substitute those numbers in place of x, y, and z and see if it satisfies the equation. So the left side here is this whole expression. It's supposed to equal 0 because we have 0 on the right side of the equation. So I'm putting the negative 2 in here, 4 in here, and 3 in here in place of z. And so that's 4. 33 times 4 is 132. 18 times 3 is 54, minus 156. Now if you add all these up and subtract 156, you don't get 0, you actually get 34. So the fact that it didn't satisfy the equation, this side did not work out to equal what's on the other side. So the fact that it's not 0 means that negative 243 is not on this plane. Let's check the 24, 4, 4 point. So we're going to put in the left side expression here, 24 here, 4 here, and 4 in place of z. And negative 2 times 24 is negative 48, 33 times 4 again is 132, and 18 times 4 is 72. And all of this does, in this case, add up to 0. So it adds up to it being exactly equal to what's on the other side. So that point does satisfy the equation. So then we would say, so the D point, the one from up here, is not on the plane because it didn't satisfy the equation, but the 24, 4, 4 point, is on the plane. And that's the end of the lesson.